Hello, my noble scholar. Let's calculus. This series is dedicated to my father and is written for students in non-science majors who have to pass calculus in order to fulfill a major requirement, but are not particularly bursting with enthusiasm at the thought of studying math due to previous discouraging experiences. The purpose of this web series is to provide the students with an alternative way to consuming math that is not only bloodless, but easygoing and pleasant, yeah, you heard it right, and may even lead them to change their attitude with respect to stop dreaming. Now, without further ado, warning. Beware, any episode may include, but is not guaranteed to have, politically incorrect jokes, alcoholically explicit content, and offensive illustrations. Or what can you do? The First Amendment, so suck it up. Disclaimer. No math professors were physically harmed when preparing this series. Sorry if you hoped otherwise. The good news. Calculus is easier than algebra. The bad news. You have to master some algebra skills flawlessly. For example, you have to know the highs and lows of elementary functions. Episode 2, Ontology of functions that are of interest to us. Imagine that you are a zookeeper, and then the animals in the zoo are functions. Some are cute and fluffy like koalas, yet others are sharp-toothed and may bite you. Your job is to take good care of them all. For that, you need to know their characters and anatomic quirks. So, meet your nurslings. The simplest function is a constant. F of x is equal to 7 or minus 33.256. Possible traps. Remember that e and pi are actually constants, not variables. They are just certain numbers with infinitely long tails, so it's more convenient to give them names rather than write down all those digits. Thus, if you see an expression f of x is equal to e, this is not a formula. This is an equation for a constant function. No matter what x is, 0 or 10 million or negative 10 million, your f of x, or the y-coordinate of the graph, is equal to the same value, e, and the graph would be a line parallel to the x-axis. The next is a linear function. F of x is equal to ax plus b. Here both a and b are supposed to be some numbers. Each function represents some pattern, and formulas are invented to capture the essence of this pattern. So every time that you see y is equal to 5x minus 3, or y is equal to minus 21.1x, 24.1x plus 58.57, or just y is equal to plain 12x, it can be described by the formula y is equal to ax plus b. The graph of linear function is a line, and let's just move to pictures. If a is greater than 0, this line will spend most of its life in the first and fourth quadrants. And you can see that this line with positive b is just visiting in the second quadrant, and this line with a negative b is just visiting the fourth quadrant. But mostly it will live in the first and the third. If a is negative, the line will spend most of its life in the second and fourth quadrant, right? And it may just visit the first or the third. If b is equal to 0, your line will go through the center of coordinates. And so here, depending on whether a is positive or negative. Well, I already said all that. A constant function can be considered a particular case of a linear function with a is equal to 0. So here is the picture again where you can look at the constant function. An interesting fact is that the equation for a vertical line would be x is equal to some number. For example, x is equal to -1, as you see in the picture here. This equation does not represent a function of x, because for one value, x is equal to -1, we have all possible values of y. However, this equation can be considered as a function of y, because for each y, f of y is equal to -1. So for y, it's a constant function. Function or not, this is the equation for a vertical line. The next are power functions. They look a times x to the q, where a and q are some numbers. For a, we would also say it's a factor or a coefficient. For example, power function would be y is equal to 65 times x cubed, or these two. With power functions, things are more complicated. If q is a natural number, we deal with very familiar functions like y is equal to x to the first, which is just y is equal to x, or y is equal to minus x squared, or y is equal to 8x cubed, and so on. Of course, when it's a natural number, we like to use n, not q. And these functions are the cream of the power functions. It's their elite. Note that when n is equal to 1, we actually have a linear function. F of x is equal to ax. So linear functions are relatives of the power functions. Okay, let's look how the power functions with natural exponent will look like. So y is equal to x. Y is equal to x squared is a parabola. You're very familiar with it. Y is equal to x cubed is a cubic function. You better know it very well. And then every time that you have x to the even power, you will have a parabola-like graph. Only the higher the power, the boxier this parabola would be. And every time that we have y is equal to x in odd natural number, you will have cube-like looking function, but the higher this number is, the boxier the cubic function will look. So now you know how the cream of power functions graphs look, right? You can also add some of the elite power functions in a constant to get polynomial functions. So you have to know what polynomial functions are, right? So you cannot have square root of x inside a polynomial function. The graphs of polynomial functions are wiggly. Well, the first order polynomial is a linear function. The second order is going to be a parabola. The third order cubic polynomial is a parabola, and then you add a wiggle. The fourth is a cubic polynomial, and then you add a wiggle. The fifth is the fourth order polynomial, and then you add the wiggle. Got it? Roughly you get one more wiggle with each additional power, except in degenerate cases when two or more wiggles occur at the same point. For example, f of x is equal to x cubed, the x cubed, all the wiggles will occur at the same point. Okay, back to power functions. If q is equal to 0, the power function will look y is equal to ax to the 0th, but x to the 0th is 1. So what we get is y is equal to a, and that's a constant function. So constant functions are also related to the power functions. If q is a negative integer, -1 for example, or -7, let's rewrite it as q is equal to -n, where n is a natural number. Then instead of ax to the q, we would write ax to the -n, and then we can spend this minus to jump the floors. So it's going to be a divided by x to the nth. For example, x to the -1st is 1 over x. 7x to the -3rd is going to be 7 divided by x cubed. A minus sign in the power is a magic elevator minus. It lets you jump the floors between the numerator and denominator. It brings down its base from numerator to denominator and then you lose the minus as in the previous examples. And also you can bring up its base from the denominator. If you start with x to the negative power in the denominator, yeah, you can jump to the numerator. The graphs of functions y is equal to x to the -n look a bit different for odd and even for the negative part of x. So, note, you will always have x in the denominator and you're going to have it in some power. So when x is positive, this is how the piece of graph looks. And graph is composed of two pieces that are separated from each other, because when x is equal to 0, they will never join. Both will go to infinity, both pieces. Okay, so this piece is very similar, but if x is in the even negative power, then you would have the second piece is symmetric with respect to y-axis. So it's the same as the first piece, right? And if you have a negative power here, you will have symmetry with respect to the origin, right? Because you will have your y is going to be negative when x is negative, and here y is going to be always positive. If q is a rational number, it can be represented by a fraction m by n, where m is whole, so it could be negative, and n is natural, so it's positive and it can be 0. It also means that you deal not only with power, but also with a radical. The base of this radical is exactly the denominator of the fraction in the power. It's going to be n. You can write it as nth root of x to the mth, or the whole nth root to the mth. These two notations are equivalent. You have to develop the skill of converting expression from radical form to fractional form and vice versa, and you have to be good at it. The power q could also be an irrational number, for example, square root of 2 or pi, but we will not deal with functions like this. I drew a picture that I hope will help you to remember how to do radical to rational exponent conversion. Now, rational functions. Rational function is defined as one polynomial divided by another polynomial. For example, this would be a rational function and that would be a rational function. Graphs of rational functions look differently depending on the actual formulas, and they can have asymptotes: vertical, horizontal, or slanted. Here are examples of two rational functions. You can see that this rational function, x by x plus 1, has two asymptotes, and its graph is broken into pieces, while this rational function comes in one piece and has only one horizontal asymptote. Exponential functions. I know you're tired, but these are our functions. We have to know them. A to the x, where a is some fixed number. Note that a is always positive and a cannot be equal to 1. And this is the definition of exponential function. In a special case when a is equal to the earlier number, e, 2.718 and so on, the function is called the natural exponent, and you would say e to the x. Other examples of exponential functions are y is equal to 6 to the x or 1/2 to the x. We can also multiply an exponential function by a factor, and that would be still an exponential function. Note that if a would have been allowed to be 1, a to the x becomes 1 to the x, and 1 in every power is 1. So this is the case of a constant function, and it's just too boring. That's why it was kicked out of the definition. Here are graphs of exponential functions. Y is equal to e to the x goes really high up. Y is equal to e to the minus x is also an exponential function. And here I wanted to show you how differently these functions will grow if you have a different base. So you can see that y to the 2x for positive x goes more slowly than y to the 5x. But for negative x, y to the 2x grows faster than y to the 5. Then y that is equal to 2 to the x grows faster than y is equal to 5 to the x. It's important to distinguish between power functions and exponential functions. See, x is in a different place, and q or a are actually fixed numbers. The latter are the fastest growing functions, so exponential functions are the superfunctions. For any power function, starting at some x, the exponential will always outrun it. Logarithmic functions are the last functions that we will look at in detail. The log functions were designed to ask the following question: a in what power is equal to b, where a and b again are some numbers. For example, you can easily solve the problem 3 to which power is equal to 9, and you would say in the second, of course. Now let's solve 3 in which power is equal to 5. And yeah, there should be some number, right? And this number is going to be more than 1 and less than 2, but how do we find it? That's why the log function was created, to find this number. So this number is going to be log of 5 base 3, and it just denotes the power to which you have to put 3, the base of the log, to get 5. And if you put number here and number here, then this expression is a number. It just, in this case, it's irrational number, but it's a number. So it's not a function. If you don't have x here or x there, it's not a function, it's just a number. You can pull out your calculator and find this number. When the base is that special particular irrational number e, we are dealing with a natural logarithm. And just for this case, a special notation is reserved. Log with base e of x is denoted ln x and solves the equation e in what power is equal to x. Remember, logs are there to help you find the power. Well, I know you don't like logs, so I made a joke to maybe make you feel a little bit better. Other elementary functions that we will not review, but they deserve an honorable mention, are trig and inverse trig functions. For example, f of x is equal to sine x, or g of x is equal to arc sine x, or the notation is sine to the minus first x. And this minus 1 is not a power, it's a way to denote an inverse function. What is inverse function? It means that we are looking for the angle whose sine is 1, and that angle is going to be pi over 2. And finally, we can have compositions of the functions above, sum, difference, product, quotient, composed function, and this is what we will be dealing with in this course. The end. And thanks.